Guys, welcome back. And we need to talk about how to fix our solvent problem. Previously, we talked about organic solvents, and we said organic solvents are very flammable, they're very explosive, they're not very good for my health, they can cause cancer, they can mutate DNA strands. So, what can we do to substitute those organic solvents out of the laboratory and put something else in their place that will still do the same job, but at least it's a little bit more friendlier to me as a laboratory worker? So a couple of scenarios have came out over the past number of years. Number one, you can eliminate the solvent altogether. You just don't even have to bring it in. And to do that, you can simply use a microwave to make this reaction go forward. A lot of times a solvent is a solution that's meant to keep something in solution in an environment, so we put heat on it and then it can react with another component. And what we've discovered in the past is that we can take these types of reactions and we can put them into a microwave, basically, and close the door and turn some radiation onto it, and those reagents will still react without the presence of the solvent. So as long as we give it some type of energy source, and as long as they can come together and do what they need to do, that's all that matters. So we can use a microwave to substitute out an organic solvent. Not every single time will this work. This really just depends on the procedure, but some of them do and some of them don't. These are often called solvent-free laboratories. So if I'm doing a solvent-free method, that's basically what's going on. Putting it into a container, putting it into a microwave, turning the dial on, let it react just like a bag of popcorn at home, and then take it out, and then it's done, basically. You've got popcorn and it's ready to eat. Next, we can substitute the solvent with another solvent that's very similar. And the objective of this is to lower the flammability of the solvent that we have and to lower the toxicity of the solvent that we have as well. So if I've commonly used a solvent that was basically done in the 1970s, and my company has always done that method over and over and over throughout the years, there's probably other updated methods that are out there now. So if I can get rid of some of those older solvents and replace them with a newer solvent that does the same thing, that doesn't catch fire as easily, or it's not as toxic as the original one, then why not substitute it? We need to make the change. We need to go more environmentally friendly, and we need to go more health friendly as well. So we need to do it. So substitute the solvents with something a little bit better. Notice I didn't say eliminate the flammability or eliminate the toxicity. If we can do that, we'll do it. But sooner or later, we're going to get to a point where we're going to find an issue or a case that when we substitute a solvent, we won't be able to get rid of it completely, but we'll be able to lower it down. Next, go small. Size matters, right? And in this case, small is preferred. So go small, meaning that in a laboratory, maybe I don't need to be using vats of chemicals in order to get this accomplished. Maybe I can cut down my reagents in half. Maybe I can cut my reagents down to a quarter of what was used. If I can eliminate at least some volume or some amount from it, then I'm making the step in the right direction. So go small and reduce quantities of stuff whenever you can. 4, use catalyst. Catalysts are pretty important, right? So catalyst speeds up reactions. And when they speed up reactions, there's a chance that I might not even need a solvent at all in order to do it, okay? So a catalyst will go into the mix, go into my container, and it speeds this process up to make a product. Those catalysts could mean that I don't have to use as much solvent, and it could also mean that I could remove the solvent completely. Maybe the catalyst is the only thing that's needed there for it to go forward. And if so, I've eliminated my organic solvent, and I've created a better atmosphere for everybody. Catalysts will also what we call eliminate steps in a mechanism. And this is going to be kind of my fifth one as well. It's kind of embedded into this because you don't need a catalyst in order to do this, but sometimes catalyst will allow that to happen. So I'm linking the two together. So a mechanism is basically the roadmap. So let's say that I'm going from Wilmington and I'm driving to Raleigh. There's all different ways, all different roads that you can take in order to get from one place to the other, right? Okay, so let's say that we have done this road trip for the same way for 10 years. And let's say that we don't take the interstate. We don't take Interstate 40. Well, that's a roadmap. That's the mechanism of how we go from point A to point B. Reactions are the same way. We go from point A to point B, and we have to go there with a roadmap, and sometimes the roadmap is kind of backward. Sometimes it's the two-lane roads that you don't want to be on late at night because who knows what's out there in the woods, right? I've seen too many horror movies to know that I don't want to be out there in the middle of nowhere. Okay, well, a catalyst could come along, and what a catalyst could do is a catalyst could be the introduction of the interstate, and all of a sudden, we can now go from Wilmington to Raleigh in half the time in a brand new route. That's what we call eliminating the steps. So the catalyst could do that. The catalyst could come in and eliminate steps completely. We don't even need to take those roads anymore. We have a more direct route in order to get there. Or I don't necessarily need a catalyst in order to do it. I can pick different solvents. And those solvents maybe could create a different roadmap for me to get to my product. A shorter route, a better route in order to get there. And if that's the case, then we'll do it. Because if we can eliminate steps in the mechanism, we can eliminate some of these byproducts and some of these hazardous things that might happen along the course of the way. And finally, number 6, we want to design reactions that give us very high percent yields. Side reactions, they generate waste. We don't want that waste around. That waste could be organic solvent. And we're going to have to handle that organic solvent product just like we handle organic solvent reagent. We want to make sure that we're handling it the proper way, that we're not disposing of it down the sink, that we're not dumping it out into the dirt, that we're doing what we're supposed to be doing with the organic solvents. So if I can increase the yields, that's better because I get a lot of product that I'm after, and that's less waste that I'm after. So for instance, if I have a 50% yield, that means 50% is my product and 50% is waste. This waste I'm going to have to do something with, and that could be organic. So what do I do with it? How do I handle it? Where does it go? It doesn't go down the drain. Does it go into a waste jug? If it goes into a waste jug, then what do I do with it then? Who's going to come around and who's going to pick it up? So, if we could increase the product yield to, let's say, 80% instead, then what happens is that produces a 20% waste and not a 50% waste anymore. So that's less amount of solvent, that's less amount of maybe organic chemical that I have to deal with as far as the waste and disposal is concerned. So those are the types of things that we need to think about in a laboratory when we start talking about organic. Organic reagents in the beginning, organic products in the end. How can we minimize that? And these are all the ways, 6 different ways that we can do that as far as a laboratory perspective is concerned. So all of this is related to green chemistry again, right? If I want to minimize the organic solvents and organic products in a laboratory, then if these are the worst environmental hazards that I'm dealing with, if I minimize those, then I'm thinking about green chemistry. See how it's all tied in together? So finally, what I can say is that in 1996, the EPA, Environmental Protection Agency, began the PGCCAP, the Presidential Green Chemistry Challenge Award Program. That is what that stands for. So I'm going to repeat it again. The Presidential Green Chemistry Challenge Award Program. And basically, it set out to target small businesses. And it said, hey, if you're a small business, if you are a small mom and pop laboratory, what kind of green chemistry technology can you produce, right? Can you figure out a way to make our lives better and our disposal better and our product and our synthesis better in a laboratory? If so, and you got this green technology that you would like to share, then submit it to this PGCCAP program, and maybe there's going to be a financial award awaiting for you in the near future. Not only did it do small business, but it also did academics as well, academic programs. So if you're in the academic laboratory, an investigator for green technology, all right? So are you working on a process that would make green chemistry better? Is there something that you're coming up with in your own academic labs that could be maybe replicated in other labs across the country to make sure that we are putting the green chemistry first? And then finally, there are 3 focuses outside of small business and academic. I'm going to call them Focus 1, Focus 2, and Focus 3. So Focus 1 is industry. So these are big major, maybe oil refineries, big major pharmaceutical companies, big chemical manufacturers. These are people that are doing this on a very large scale. So there's an industry sponsor for what we call a green pathway. And then there's an industry sponsor on green conditions. And then another industry sponsor on the design of green chemicals. So basically it targets all 3 facets of what we should be thinking about in a laboratory. So design of green chemicals, is there something that we can produce or that we can come up with to substitute common solvents out for these newly designed green chemicals that are not going to be an environmental hazard? The green conditions and the green pathways, those all relate to basically the reactions. So the pathway and the conditions. So can we lower the amount of heat? Can we lower the amount of water? Can we lower the amount of pressure in order for these reactions to take place? If so, then my conditions are a little bit better. The pathways are the mechanisms. So is there a different way to synthesize certain products that are very commonly made in the industry environment that is a little bit greener and a little bit better for me? And if so, then all 4 of these get awarded every single year. So it kind of acknowledges the fact that we are working toward green whenever we can. We are not Mother Nature haters. We do really want you to drink clean air, and we want you to breathe clean air, and we want you to drink clean water. So we're not setting out to poison anybody. And it seems like that's a lot of times the scientific community, that's the slack that we get. So anytime that we can kind of brag about ourselves, about look at us, we're trying to be environmentally conscious here, then we're going to do it. And this program kind of highlights and showcases some of that initiative. So I want to show you maybe some recent award winners. And here's a picture of the Green Chemistry Challenge Award winner, and just a little bit about some of the previous awards that have been given out. So up at the top, you're going to see a soy-based or a renewable feedstock chemical to prepare toner for laser printers and copiers. So laser printers and copiers are, of course, they're never going to go away. We're always going to be printing stuff, right? So as far as the laser printer and copier is concerned, is there a chemical that we can do or we can make to make this process more environmentally friendly? And the answer, yeah. This company came up with a soy-based chemical to prepare the toner. So this is a renewable feedstock, meaning that soy is grown. We can harvest the soy for many different number of reasons, and one of those would be to take this kind of byproduct of soy that maybe is not even used and convert it over to a chemical that can prepare toner for your printers. The next one is new synthesized pesticide that replaces an organophosphate pesticide with a catalyst that saves energy and recycles solvents and reagents. So that's pretty important, right? We get this new pesticide, and it replaces an old one that was organophosphate-based. And those are kind of some of the nastier ones, for the environment at least. So we don't want to be pumping out this phosphate pesticide out into our rivers, lakes, and streams. So we get a new pesticide that replaces that old nastier one, and we get a catalyst, and it saves energy, and it recycles the solvents and reagents so we can use them again later down the road. It's not just wasteful. So we get a better synthesis route, we get products that we can recycle and reuse, and we get a better pesticide as the end result as well. So of course, that's all green through and through. The next one says new method for making the precursor for a Suzuki coupling reaction designed to avoid hard conditions and generate less waste. So who cares if you don't know what the Suzuki reaction is? That's not the point here. You'll eventually learn about that in organic chemistry much later down the road. But a new method for making precursors. That basically means we've got these starting products, and is there a way that we can get these starting products a different way that's much greener, that's maybe much cheaper than the original plan of how it's always been used? And this basically said yes. We can come up with those starting products. We can do those in a better way, in a greener way, and these starting products you can then use for that Suzuki coupling reaction. So we don't have to give you very high acids content and all of the other conditions that are out there in a laboratory. It's much better for the laboratory worker. It's much better for the industry as a whole because no longer do we have to expose these personnel to these hazardous environments in their work. And it generates less waste at the same time. So the product that gets pumped out in the end, that product is actually used. And what's not product that stills waste, well, it generates less of it. So we might not fully eliminate it. It might not be recycled. It might not be reused. But maybe we went from that 50% waste to a 20% waste. And if so, then we've put green in the forefront. That's what we're always after every single time. So you can actually go just search for the previous award winners under the EPA.gov website, and you'll be able to find them. So I give you the link here. If you want to pause the video and kind of type that into your search bar and put it up on your web browser, you'll be able to scroll through and see what other people are doing too at the same time. But that's just a short, brief list of some of these recent winners and what they've done. All right. Okay, so finally, we're going to end with RAMP again, right? We want to recognize the hazards of the solvents, especially with organic in mind. We want to assess the level of risk from the hazards. So how dangerous are they? Do I know that going into the picture? That's the assessment part. M is minimize. So I want to minimize the risk from the hazards. So I want to reduce the quantity that I'm using. I want to substitute them for something a little bit safer. I want to maybe choose something that doesn't give me a lot of waste at the end product. Whichever way that goes, I'm minimizing my exposure to the hazards. And finally, P is prepare. prepare for the emergencies. And again, organic chemicals, you know what those are going to be now. They're going to be flammable. They're going to be very toxic to the human body. You don't want to breathe them in. You don't want to take a bath in them. You don't want to pour them on your skin. These are kind of bad news bear chemicals that are in the laboratory, and it just so happens to be the most common. So that's the rant for organic solvents. So keep calm. It's just organic. That's all it is. But I want you to keep in mind that in an academic laboratory, we try to, again, take all of these things into consideration. We don't want to expose you to something hazardous. We don't want to expose you to something that's going to give you cancer. And because of that, we have taken these green initiatives already, and we've chosen the correct laboratories for you to do that's still relatable to industry for that purpose. All right? So you can kind of say, trust us, we kind of know what we're doing sometimes.